So, hello again. This time I get to well, you get to see the work I do rather than other things. Although it's true, in this case, I'm far from the expert on this project. Hayward, Godwin and Tamaryn Menneer really drive the project forward at Southampton with Simon Liversedge and Nick Donnelly. They're all vision scientists. And it has an international dimension in that we collaborate with Kyle Cave at UMass Amherst as well. And one of the reasons for doing this talk is because they don't so often get to describe the methodology behind the experiments they do, and that's one of the things we want to do today. So what's the motivation? So like many things, from my point of view, this started off with a curiosity, a question about how on earth do we do X, which is often how I go and ask the vision scientists I know, why on earth do we do this or that? And in this case, it was how do we see things and how does 3D help in the process of visual search? And the driving application for me really was the second one, which was radiology in hospital. We'd done some work with the Freeman Hospital in Newcastle in the UK on MRI and CT scans. And there was huge enthusiasm from the consultants and the radiologists about the use of 3D to help them understand 3D scans better. But I didn't really know a lot of information about if that would work and if the targets they were looking for would really be visible. And at the same time, in Southampton, they've been looking at for a while this X-ray security screening problem at airports. And how do you speed up the search in these types of images? And because they're very similar types of images, they're transparent, they have depth, it seemed an interesting thing to put together into a project, which we did. A more everyday example that might help you understand some of the variables we've looked at is that of finding your keys on a cluttered desk. So like these ones here, they might be partially visible, partially occluded by things. But like these ones here, which are much harder to spot, they might not just be very occluded by things, but also occluded in depth. So the things layered up might well be things in different depths. And so these are the two things we were trying to look at in this set of experiments, how occlusion affects your ability to search for targets, and how depth might help your ability positively to search for things in depth. And the key application really that drove the funding was the security screening at airports, which many of your bags will have been through on the way here, and whether we could do something to improve the accuracy of target detection for the security screeners who look at these images. This is a typical visual search stimulus that was used by the Tamaryn and Hayward, a typical laboratory stimulus. You're looking in this thing for some kind of target that's different, and in this case it's this T target from these not quite T targets. And in a typical experiment, these will be presented to subjects a lot of times, and the target is often only present in about 50% of the trials, or exactly 50% of the trials. Alongside this, some terminology you need to know. Sometimes these are single target searches, so you're being asked to look for a single target. There's only one in the image, but you're being asked to look for one type of target. And in other searches, you're given two possible targets that are there, so either knives or guns, and you've got to search for whether either of those is in there. And it's known that this gives you a cost. If you're asked to search for two different things, you find that harder. So your accuracy in finding them goes down, and if you're not trained, your time takes longer to find them as well. So that's the kind of visual search that they started off with and that we worked on in this set of experiments. So the experimental design, we wanted to look in detail at the influence of this overlap of things on top of each other and depth in the performance in these types of visual search tasks. Previous studies had looked at overlap and suggested that your performance is affected by it, but they'd not precisely controlled the amount of overlap in the trials. So it was one of the things we wanted to do here. And similarly, the use of depth has been looked at before in visual search, but the results are conflicting. Not all the time, and it's certainly not all the time in all stereoscopic experiments that people do that depth helps. And it was the same here in visual search. It hadn't always helped. And we wanted to try and control both the depth and the occlusion quite precisely in this series of experiments. If anyone's seen John McIntyre's set of papers on 3D and what is it good for was the title of his paper here. You'll know there's a whole series of possible tasks you can use 3D for, and some of them you're much better at with 3D, and others it really doesn't help as much. So there are sets of things that we were setting out to measure, which are fairly standard in visual search. Response time and response accuracy were the two first ones. And we predicted that in our experiments, an increase in overlap, so the more objects are overlapped, the response time will get longer. It'll take you longer to sort these out, and your accuracy will go down. So the task gets harder the more overlap you see. And we also predicted that with increasing amounts of depth in the scene, this would decrease the response time and increase your accuracy. So the task gets easier if we can put depth in it, if depth is part of the issue in the overlap, the difficulty of detecting target objects in overlapped scenes. Those of you who know Simon Liversedge will know that he's a great eye movement expert and does lots of studies on eye movements, particularly in reading, but also in visual search. So at the same time as running these search trials, we in some great detail tracked eye movements to give us an idea of this, how your brain responds in real time in visual search tasks. And to do that, there's a set of terminology that the psychologists use. Here, the two types of errors that happen when you're looking around a scene and searching for a target. The first one is you just don't see the targets, so you fail to detect a target at all. And the second one is you look at the target, but you fail to identify it as the target. So these are errors of perceptual selection and errors of perceptual identification. And again, like on the previous slide, we predicted that with increasing occlusion, both types of errors would go up, and both types of errors would be less likely with increasing depth. So that's the kind of the set of things that set the scene for what the experiment's about. So then the question was, how do we build an experiment to test occlusion and depth in visual search target trials? And how do we make it both controllable and representative, environmentally valid for the search tasks that we're interested in? So we came up with this set of stimuli. On the left, there's opaque polygons and transparent polygons. So you remember we're interested in X-ray images, where very often it's layers of semi-transparent or transparent things that you're searching through. So as well as having an opaque scene, we had a transparent scene. And for the X-ray images, we actually had a bank of X-ray images and target items, which we used. And then we had to have an opaque equivalent to that. And because there wasn't an exact opaque equivalent, we had a set of real-world objects that were photographs of objects to go with that. So there were 4 types of image in the trials, intended to be representative of and controllable in different ways of the original applications. And then within these different types of environment, there's a set of search targets. So in the within the polygon style images, each participant got a different pair of targets to look for to reduce any kind of effects of a particular polygon shape having a particular influence on the search. And so each participant would search for one or two of the 2 target polygons that they were given in the polygon images. In the X-ray images, they would search for weapons, so particularly guns and knives, and IED devices. And I believe we're not really allowed to show IED device X-ray images, which is why there isn't one there. But this is the kind of thing that you're looking for in X-ray images for guns and knives. And then the real-world images, we also had sets of toys, as well as knives and guns, that were the target images given to participants to look for. So the different types of targets were tuned to the different environments that we were searching through. This was the environmental hardware setup. So a number of challenges. You can't really buy 3D TVs anymore. So we had to buy a number of these 3D TVs at the time because the rate that we've changed through them is quite quick. So these are Hyundai W243Ss, which use linear passive polarization. And now you can't buy them, but at least we've got a few of them to use in our experiment still. Linear gives a better crosstalk profile than circular. And although it's true that your head tilt affects it, you'll notice the participants on a headrest, so their forehead and their chin are supported, so they're not going to be able to move their head a lot. So the crosstalk issue isn't really there. The stimulus are shown on there. They wear polarizing glasses in all conditions. And they sit 80 centimeters away from the TV with the eye tracker down here, which is capable, using infrared light, of tracking through the polarizing glasses. So we're still tracking their eyes as usual. And they hold a handheld device here in order to indicate whether or not they've detected a target. On the other side of the room is the experimenter, and he's using the control system for the SR iLink 1000 and recording live video of where people are looking and what they're doing, so that we can go back and analyze afterwards the eye movement behavior, as well as the results of the experiment. In order to drive that, we needed to create a set of images for the trials. It turns out there was 1,728 images required for 32 participants. And each participant, had to undertake 6 hours of trials. So it was quite an onerous task for each participant, and keeping them for that long over time was a challenge for Hayward, I know. But these are the sets of variables that we changed. So we changed overlap of all the types of stimulus from 0 to 90% of the object's area. We changed the number of objects in each stimulus. There are either 24 or 40 for people to look for. Obviously, we changed whether there was a target there or not. Complexity was the number of possible overlaps at any one point, 2 or 4 objects overlapping. I'll come on to the amount of depth in a minute, but it was either a 3D image or it was a 2D image with no stereo depth in it. And the search type, whether people were looking for a single target or dual, possible dual target search. So that led us to having this 1,720 images. In order to control the data collection side of the experiment, we could use the standard SR Research Experiment Builder software. And that was just given a list of trials, a list of the images in pre-interlaced 3D format. And also, the very tedious task for us was to, well, not for me, for Hayward and colleagues, was to highlight all the regions of interest for eye tracking. So every shape and polygon had to be highlighted so the eye tracking software knew where they were. And then the other side of that was to build custom software to generate these nearly 2,000 stimuli images. So all of the variables on the previous slide are options in the software, and it could go off and run them. And it needed to run in parallel because the time it took to generate these images was substantial. So we had it running on multiple computers to generate in the end. And then it saved the state in XML files, so we could use that, as we are in fact still using, for analyzing the results using R. 2 quick technical points. Generating controlled overlap. Each overlap was formed from a number of objects, and they were gradually brought together, slightly jittered at random, until a measured amount of overlap was there. So if we were only 45% overlap, we actually measured the amount of overlap between the polygons. And we could possibly have had an analytic solution for that, but that was not going to work for the X-ray images, so we did a pixel measuring solution. Once we created the overlapped image, we then jittered the position in the grid of all images on the screen, so we didn't show a completely regular pattern at every stage. And the second part of that was generating the stereoscopic images. I took for granted that everyone knows how to generate stereo images, as I would, but it turned out that everyone doesn't know how to generate stereo images. And in the original version of this, we took even lines from the left image and odd lines from the right image, and interleaved those to form the stereo pair. When you do that, you get some horrible aliasing effects on the textured real-world images because you're sampling lines of texture across teapots and things from different parts of the image. So we worked out, after reviewing a preview of a set of 100 or so images, that we need to just take them from the same line, which I would have kind of done automatically had I been doing that part of the software. And in terms of putting depth into these images, we generated planes of depth 4 pixels apart in disparity, -6, 2, -2, and -6, -2, 2, and 6 pixels in front and behind the screen. So there were 4 possible layers for things to be in. So, where are we? We've run a lot of the trials. Notice my numbers are going red, so I'm coming to a handy end. We're in a lot of the trials, and we're currently analysing all the results that are coming back from them, and there's a lot of them, so it's taking a while to go through all the R. But what we can tell you now is that for opaque polygons and single target searches, where you're just looking for a single target, as you would expect, increasing overlap does increase response time and decrease response accuracy, which is also what in agreement with the literature. Depth, the situation's a bit less clear, so adding depth into these complex images does speed up the time to make the decisions and detect a target. So that's good in that if you're processing lots of bags through an airport, you want to go quite quickly. But it doesn't increase accuracy. So if you're given an arbitrary amount of time to do this, you'll still get the right answer if you're given it more time in 2D. So the benefit of 3D here seems to be a speed up in response time. I should say, we thought about this a while. This is the case, particularly in the more complex scenes. So there's more targets and more overlap. Depth does give a benefit. When there's less complex scenes, depth in this case isn't giving a benefit. And when we sit down and think about it, that might be for a good reason, in that these are fairly clear shapes with fairly clear boundaries, and in real X-ray images, things are a lot fuzzier. So it'd be quite nice to take real 3D X-ray images and try the same thing again. But for this, we're still working through all the results, and there'll be full results coming out soon. But a small plus for depth there. One of the things we're going to do next in the project is look at whether we can train security screeners in the form of students in 3D to improve their performance in 2D. So if we can get a transfer of this benefit, so if they get a better idea of how things work in 3D, can their performance improve in 2D? And last slide. Thank you for your attention, and thanks to our funders at the Economic and Social Research Council in the UK.
Thank you.